So hello everyone. In this video, I wanted to make a brief example into what is the effect of designing PID controller, no? What is the effect of the proportional, the derivative, and the integral actions? Okay. So to explain this, I will be using as an example a spring mass damper system. So suppose that we have the following system. No, we have here a support, no, that is fixed. Here we have the constant of the spring, and also here we have a damper, okay, with the following constant, and we have here a mass. Okay, this is the mass. We are applying a force, okay, and we are measuring the displacement, okay, of this mass, and this is the positive direction, okay. And if we generate a transfer function that relates the force with the position, no, this applied force with the position of the mass, we can obtain the following transfer function in the S domain. Okay, we have x of s divided by f of s. No, this is the transfer function that relates the input force with the displacement of the mass. And this is equal to 1 over m times s squared plus b times s plus k. Okay, this is the transfer function, no, for this spring mass damper system. Okay, so basically what I'm doing here in this MATLAB code, okay, let me erase this, is to simulate the behavior of this spring mass damper system. So to this end, I am placing here a vector for defining the zeros or the coefficients of the numerator of my transfer function of this spring mass damper system. I am defining a value for the mass, a value for the coefficient of the damper, a value for the constant of the spring. And with these values, I am defining a vector, no, for the coefficients of the denominator of my transfer function. And I am using this function called df to generate the transfer function of this spring mass damper system. Here I am computing the eigenvalues or the poles of the system using this function. And I am here plotting the step response of the model. Okay, so I will run this code. And, well, it's taking a little bit of time to run. Let me see what is happening. Well, it's running the model here in MATLAB. It's a little bit slow. But basically, I want to transfer this model, no, this transfer function model into Simulink, okay? Because I already designed these PID controllers in Simulink, and I want to show you how the addition of these elements in, well, the use of the proportional, the derivative, and the integral actions affect the closed loop response of the system. So here I upload the open loop response of this spring mass damper system. Remember that the open loop response is basically taking here the system, no? This is the spring mass damper system, okay? And we have here the output, okay? That is the position, and the input is the force, okay? So basically this, I am using this step open loop response. Okay, so basically that means that I am placing here a constant value as the input force, okay, for times greater or equal to 0, okay, and I am plotting what is happening to the output of the system based on these conditions. Okay, so this is the what I did previously, or the graph that I showed previously is basically the open loop response of the system. Now, if you go here to Simulink, I will open Simulink. I have already created a Simulink model that has this PID controller. No? So this is well, MATLAB is opening the Simulink model. We need to wait it a little bit. So here in this section, I have divided the Simulink model into 4 sections. At the top, you can visualize the open loop response of the system. And the three main components are the following. Here we have the step input, okay? But remember that the step input is basically a constant value that is zero for times lower than zero, and it's one or any value for times greater or equal to zero, no? So this is the value of the for input force of my spring mass damper system. Here I am using this transfer function block to load the parameters of my transfer function. So I need to input the coefficients of the numerator of my transfer function and also the coefficients of the denominator of my transfer function. So I am using the same vectors that I've used previously. And here is a scope. A scope basically is like an oscilloscope in which I can measure the response of the system. Okay? And I think that's it. So we can run this model. We can click here on the start to simulate the open loop response of the system. Okay, so you can hear or visualize here at the bottom that MATLAB is compiling the model and then it runs the model over time. I can place here in stop time the maximum time in which I am simulating the response of the system. So I have set this value to 100 only for illustration purposes, but you can set this value depending on the needs, no, of your analysis. Okay. But now we have run the simulation for this open loop response, and you double click on the scope here, and you will see again the open loop response of the system. Okay, we need to wait a second until Simulink loads the plot. But here we have the simulation. You can see that, as expected, for a spring mass damper system, we have certain degrees of oscillations due to the constant of the spring value that I selected. And also you can see that here we have a certain damping due to the damper that the system has, okay? And also this damping depends on the value of the B value that I set, okay? Or this damping coefficient of this spring mass damper system, okay? So this is the open loop response. But I want to design a controller that allows me to control the oscillations of the system, but also to control the speed of the system and also that it follows the reference that I want. Okay. So, and also I wanted to show you what is the effect of this PID controller. Okay. So here in this part, well, that is like in this orange or pink color, I have designed the controller, no? Or this closed loop system. Basically, you can observe here that I place again the same transfer function, okay? That is basically the transfer function of this spring mass damper system, but I have already placed a controller, okay? In particular, I am only using the proportional action, okay? And I am using this cable to simulate the presence of a sensor in which I am measuring the position of this spring mass damper system, and I have the desired value, okay, or the desired reference. That is basically the position that I want to set for my system, okay? And I am comparing, okay, this reference value with the actual position of the system. That's why I'm connecting the output of the system with this comparator that basically compares the reference minus the actual position of the system. And at the output of this, I will get an error, okay, an error signal that I'm using to fed this proportional controller, okay? So the result of this will be Kp times E, okay? So this is basically the result that I am simulating with these blocks, okay? And I am doing the same in the bottom, no? The only difference between this one and this one, no, the one at the top and the one at the bottom, is that basically I changed the value of the proportional gain. Here I am using a value of 2, and at the bottom I am using a value of 10. And here in this scope, I am comparing the reference, the response of the system when using a proportional gain equal to 2, and the response of the system when I use a proportional gain equal to 10. And I can plot the response, no? If I double click here in this scope, I can see the comparison of the different responses, okay? So in green, you can observe in this graph the value of the reference, okay? This is the position that I want to achieve, okay? And in blue, you can see the response of the system when I am using a proportional gain equal to 2. And in red, I am showing the response of the system when I use a gain equal to 10. So based on this comparison, you can see that when you have a very small proportional gain, you are not reaching the reference that you want, okay? But when you increase that gain, okay, you can see that based on this red signal or this red response, that we are reaching a little bit the reference. We have certain gap, but at least we are getting closer to the reference that we want, okay? So basically, what we are doing with this proportional action is to increasing the the energy that is input into the system. Okay? Or in other words, it's like we're adding some virtual spring to the system. Because also you can observe here that when we increase this gain, we are also increasing the oscillations, okay, of the system. Now, if you compare when I am using this gain equal to 2 and this gain equal to 10, the oscillations of the red signal are bigger compared to the blue one, okay? So by applying this proportional controller, we are input more energy into the system, okay? But also that can help us to get closer to the reference that we want. But at the same time, we have this problem of increasing the oscillations. No, it's like adding another spring to the system. Okay, that's why we are increasing the oscillations because we are adding like this virtual spring that is increasing the oscillations of the response of the system. Okay, but well, having a proportional action is sometimes good, no? Because at least we can observe here that we are increasing the that we are getting closer to the reference. Okay, but with the effect that we're increasing the oscillations. Okay, so you need to be careful with that. Okay, so how can we get rid of those oscillations? Well, if you want to get rid of the oscillations, you can add another damper. But instead of doing that, we can apply the derivative action. So in this part of the Simulink model, I have make a similar process. No, I have designed a PV controller. Okay, here you can see that I have the proportional gain, but now I have added this derivative controller. Okay, that it basically consists of computing the derivative of the error and multiplying that error by a derivative gain. Okay, that is this value that I am placing here. And at the end, I am adding the results of the proportional and the derivative action. Okay, so mm, well, and this is what we call the proportional derivative controller. No, I have write this in this section, and I have performed a similar process. No, at the bottom, I have again the proportional and derivative controller, but I'm only changing the value of the gains. Here I am using a proportional gain equal to 10, and at the bottom I am using a derivative gain equal to 5. So I increasing the gain of the derivative action. So if we visualize the response of this system, okay, let me double click here. Okay, well, you can see the following behavior. First, this is the reference in yellow, and in red, you can see that this is the response of using the proportional and derivative controller, but here I am using a derivative gain equal to 5, and in blue, I am using a derivative gain equal to 1. But based on this, if we compare these graphs or these plots with the original one, no, when we only use the proportional controller, you can see that we have reduced the oscillations a lot. Okay, so basically what we are doing with this derivative action is that we are reducing the oscillations of the response of the system. Okay, in other words, we are adding more damping to the system without altering the actual system. No, we are like generating this virtual damping that basically reduces the oscillations of the system. In fact, you can see that if I compare the blue signal in which I use a very small derivative gain, well, the reduction in the oscillations was lower compared to the red one, in which I increased the derivative gain to 10 and the oscillations almost disappear. And the reason for that is that by placing this derivative action, I am reducing the oscillations of the system, or in other words, I am adding more damping or more friction to the system. Okay? So that is the effect of the derivative action. Okay? But before we move into this, you can see that we still have this gap. Okay, we have a separation between the reference that I want and the actual response of the system. So we need to find a way to reduce this gap. And to reduce this gap, we can use integral action. Okay. So this means that we need to place more energy into the system. Okay. But we can see that if you add only the proportional action, you will increase the oscillations. Okay, so there is a better way in which we can add the adequate amount of energy that we need in order to reduce this gap to zero. And one way to do that is to use the integral action. Okay, so here in this part, just let me a moment. I designed the proportional, the derivative, and integral action of the PID controller. Again, this code is very similar, or this diagram is very similar to the previous one. The only difference is that here I am considering the integral action, in which I am considering integral gain equal to 1. And this is the symbol for an integrator here in Simulink. No? And basically, this tells Simulink that I want to integrate the signal that comes from this comparator. Okay? And at the end, I am adding the result of the three components, no? The proportional, the derivative, and the integral action. Okay, and I am input these elements into as an input to the system, no? That is like the virtual value of the force that I need to apply to this spring's mass damper system. And at the bottom, I am doing basically the same. The only difference is that instead here I am using integral gain equal to 3. And in the original one, I am using an integral gain equal to 1. Okay. So again, we can observe the response. Okay. So you double click on the scope and you can see the action. In fact, this in blue is the reference, okay, that I want. And in yellow is the behavior of the response of the system when I am using this PID controller, but instead I am using the integral action equal to 1. In this case, the gain for the integral action is equal to 1 in the yellow one, and in the red one, I increase the integral action equal to 3. But you can see that by adding this integral action, I have reduced the gap between the reference and the actual response of the system. Okay? So that is the goal of the integral action, to reduce the error, no? Or this steady state error of the signal, no? Or the difference between the reference and the actual response of the system. Okay? But here you can see that um, we are increasing a little bit the oscillations. Okay, at least for the first controller, since I don't have a very high derivative gain, well, the oscillations are a little bit bigger compared to the red one. So that is an effect of the integral action, no? That, well, you can get and you can reduce the error between the reference and the response of the system a long time, but also you have the effect of increasing the oscillations. And the reason for that is that the integral action is quite similar to the proportional action, but in this case, we are generating these oscillations, or we are inputting more energy based on the accumulation of the error, okay? Because remember that integral action basically adds the error over time, okay? It's basically performing a summation of the error, okay? And based on that accumulation of the error, we are adjusting the input energy into the system, okay? But also, I wanted to mention that, well, you need to tweak a little bit these coefficients, no? Because the values that I propose are not the best ones. In fact, there are methods to design these coefficients or determine the coefficients, like the Seeger-Nichols method, okay? Or even you can use some optimization techniques like heuristics to try to find the best values for these proportional, integral, and derivative gains of the PID controller. But at least the important thing is that you understand what is the fact, no, of adding these three PID controllers and um, and see what is happening to the response of the system. Okay. So what else we can do? Okay. So here in this final part, what I did is to compare the proportional action with the proportional and derivative action, and also what is the comparison with the proportional, the derivative, and the integral action. Okay, I'm basically combining the three effects into one graph in order to see what is the difference between them. Okay, and also I wanted to mention that a good way to design a PID controller is to always start by adjusting the proportional gain, then you add the derivative action, and then you add the integral action. That is one of the reasons that I presented the controllers in this format. No, you can first adjust the proportional gain, then you adjust the derivative gain, and then you adjust the integral gain of the controller. So you double click on this scope, okay, and well, you can see the effect, no? We can compare them more easily. In yellow is the reference, okay? In blue is when you only add this proportional controller, and you can see that we are basically increasing the oscillations, okay? But we are not reaching the reference. Then I am using, well, in the red signal, we are using the PV controller or the proportional and derivative controller. And you can see that we have reduced or we have damped the oscillations of the system. Okay, but we are not reaching the reference. So I can add this integral action in order to reduce the gap between the response of the system and the reference that I want, or the position that I want for this spring mass damper system. Okay, so based on this, you can see that in the green one, I have already reduced this gap that considers the proportional, the integral, and derivative action. Okay, and also you can see that I have a small overshoot here, but at least the system is reaching the desired position very fast. In fact, you can see that it reaches this position like in around 5 seconds. Okay. So that is another characteristics that sometimes we want to control, no? How quickly we can move the system into the position or the trajectory that we want. Okay, so you can see that, well, basically we are doing a good controller, no? And that's why we need the simulation, or that's why you need to know what are the dynamics of the system, because based on these dynamics, you can adjust the controller that you need, okay? So this is only a brief introduction to the PID controllers in order to study the effect. Later, I will try to make some more videos related to this topic. So see you later.